Okay, we're back in linear algebra. We're going to finish out section 1.2, lengthening our list of examples of vector spaces. So you can see I've got some lit there. We're going to look at detail at matrices, functions with values in any field. We'll talk specifically about polynomial functions. Another important example, but I'm going to leave it to your reading. It's an example in this section of the book is sequences, but I'm going to leave that one to you. Okay, also two results, theorems 1.1 and 1.2 in this section. We will discuss methods about how to prove those things as we get going in our course. We can still make some comments about how to write mathematical proofs. Okay, so I'm going to do this a lot in this lecture. I kind of pulled some stuff that I can refer to out of the text. It looks a little bit nicer on the slides, and I'll just narrate it as we go. So the first example is about matrices. I'm going to assume you know what a matrix is, but just for the sake of completeness, let's look at this page here together. So it's in a rectangular array of entries, a matrix with entries in a field F. So again, that field is usually the field of real numbers for us, but it can be any field in general. It's a rectangular array of numbers. It has rows. If you fix the first index, that's our convention. If you look at an entry aij in here, if you fix the first index I and vary the index j, then that's in a row. So the first index, there's m rows in this matrix. I varies between 1 and m. All right. Likewise, if you fix the second index, let me fix it at 2, and let I vary from 1 to n, that's called a column. So the column index j varies from 1 to n, and those m times n numbers arranged in rows and columns like this dictate a matrix. Those are the entries of it are called entries. They come from the field F. Like the author says, we're going to think of rows as being vectors in our tuple system, Fn. Think of columns as vectors in Fm. So it's an m by n array of numbers. If all the entries are 0, we call that the zero matrix. The book's notation for them, matrices are denoted by capital letters. And if you write that aij like that, it means that that's the entry, that's an element of the field F that's in the ith row and jth column. Okay, if n and m are the same, then we call it a square matrix. So it's got the same number of entries in the rows as the columns, so it's a square. It's not longer than it is tall or vice versa. Two matrices are the same if and only if they have the same entries for all possible values of the indices. And that's called the size. The size of the matrix is how many rows and columns it is. So two matrices of the same size, you add them component-wise, just like you do vectors in FM. Right, so you just take the entries in the corresponding places and add them together to produce a new matrix of that same size. In particular, if let's denote like the book does, let me just draw it to your attention here by highlighting it. This m sub n times m of f, that just denotes the set of all possible matrices with entries in f. Okay, so it's an infinite set if f is infinite. It's all possible matrices. And then he's defining two operations, matrix addition and scalar multiplication, by these formulas. Let's look at them one at a time. So he's saying if you take two matrices, what's this formula saying? It's saying that the element in the ij entry of the sum, because that's what you have to tell me for a matrix, is tell me all these numbers. You get it by adding the ij entry of A and the ij entry of B. So again, those have to be the same size, and that makes sense. Likewise, the element of the ij entry over here of C times A, C being a scalar, is, well, you just take C and multiply it by the ij entry of A. So you just multiply every number in there by that same scalar. So you can pause the video and look at these two examples, but how he's computing these things, this -3 over here, whoops, that was disorienting, this -3 over here, it's just the sum of that 2 and that -5, and so on for the other 5 entries. Or down here, you multiply a matrix by -3, you just multiply every entry by -3. That's the scaling of it. So you're not surprised that those component-wise operations of matrix addition and scalar multiplication, they make it a vector space, right? I'm not going to go through the verification of all the axioms. I've just kind of written here on this slide what justifies it. It'll all boil down to the component-wise operations in the field. Right? When you're doing these operations to matrices, you're basically just doing something with field elements where all those things are true. So that'll justify the vector space axioms, just like it did for the n tuples. right? Some special notation, if n and m are the same, the square matrices, it's kind of a pain to write m, n, n. So we're at the n once. So if you just see one variable there, like m sub 3f means 3 by 3 square matrices. Okay, second example, functions. I'm assuming you took Math 240, you've taken calculus, you know what a function is. It's a rule between two sets called the domain and codomain. So if the codomain happens to be a field, then the set of all functions from any set S into that field is a vector space. And that's what this slide is about. So that's the notation for it. The author's denoting by this fancy looking F with the S there, the functions from S to F. Again, F is any set in the world as long as it's not empty. F has to be a field. And it's just the set of all functions to it. So two functions are the same, if they do the same thing to every input, just like usual. And it's a vector space under these two operations. You add two functions, you're used to this. You add two functions, f and g, by adding their outputs. That makes sense because f of s and g of s are elements of a field. You can add them in the field, right? If that's usually the field of real numbers. This just means add this number to that number. It makes sense, so it defines a function. Same thing for the scalar multiple. You just scale the output, right? So you're used to, in calculus, the example where s and f are both the set of real numbers, right? That's just the set of functions from R to R. Your functions like sine of x, cosine of x, all the polynomial functions. There's lots of functions. The domain is the real numbers, the codomain is the real numbers. Those are examples, and you add in calculus. This formula is exactly what you're used to when you add two functions. Same thing for scaling them. Here, let's verify some vector space axioms. I've kind of written it out here so I can go fast, but maybe I want to verify the commutativity of addition. So the structure of the proof, I have to choose any two elements of my proposed vector space, and I need to show that their a sum is the same in both orders. So these are functions. So if I'm going to show two functions are equal, I have to show they do the same thing to everything in the domain. So I'm picking an element of the domain here. And then I look at, well, what is f plus g of s? Well, by definition, it's this thing, f of s plus g of s, which in the field f is, of course, equal to g of s plus f of s. I can switch the order. And that, by definition, is the g plus f of s. Okay, so because that's true for every element of the domain, that means the two functions are equal. That verifies the first axiom. I'll let you stop the video. I won't even comment on this, but I've written out a proof there of the sixth axiom, that if you take the product of two scalars, scale a vector by it, then you end up getting this sort of product of the scalars in that order. It's a associativity looking thing. I'll leave you to write the details of that to keep the video shorter. We'll give some special notation. It's an important case when it's real numbers to real numbers. We'll write it like that, r to the r. It's easier to write than that f thing. So r to the r is the set of all functions from r to r, and it's a vector space. It's a big vector space in some sense that we'll make precise later. Okay, next example, polynomials. I'm going to assume you know what a polynomial is. A polynomial expression is something that looks like this. If its coefficients are over a field f, it just means those things, those numbers, usually if it's the real numbers that are in front of the powers of the variable, are from that set. So a polynomial over the real numbers is a polynomial whose coefficients are all real numbers, and so on. All right, so those things are called coefficients. There's one of them that's not zero, that anything past it is zero. It's the sort of coefficient of the term with the biggest exponent, if you like, and that's called the degree. Unless all the coefficients are zero, then we call that the zero polynomial. It doesn't have a degree. Or this author says that its degree is -1, but we won't really ever use that information. All right. So, and you can add polynomials together. Here I took it from a slide to make it a little bit easier, but in order to add them together to give a formula, I have to do a little bit of trickery, or the author does rather. So he takes two polynomials. This one, f, has degree n, and the b and g has degree m, right? And so the author says, well, let's suppose, without loss of generality, that m is less. So he sticks on, quote unquote, some more coefficients to g to make it be the same length. bm plus 1 up to bn, let's just call them all 0. So g still has degree m, but we're just writing these kind of placeholders, right? So then we can write it in this form where the length is the same. That was the whole point of all of those shenanigans, is to get the length to be the same, right? Then you can define the sum of the two polynomials, that's what's going on down here, by just adding the coefficients. And it makes sense. You're adding just zeros here, so you're not going to change those coefficients where you added placeholders. But given that definition, you can add any two polynomials together. And you can also scale a polynomial. You just multiply all the coefficients by the scalars. I'm going to leave it to you to check the vector space axioms. They all happen because you're just doing stuff with things in the field. Again, it's starting to be a familiar theme, but that makes a vector space, okay? And it's kind of humble down here in the corner. I'll highlight it so you don't miss it. The polynomial vector space is denoted by P of F. P for polynomial. Important vector space for us. Important example. Okay, so that's some examples. I said you could read sequences yourself. It's an example written in your book. Maybe it would be helpful for me to write that. Don't forget about sequences. And now let's check out some theorems. This video is getting a little bit long, so I'm going to kind of go through this a little bit quickly. But the first theorem is called the Cancellation Law. And well, let's check it out. So you take a vector space. And you have three elements. I'll just kind of walk us through the statement of it, X, Y, and Z. And they can be any three elements. So important, look at that quantifier, X, Y, and Z, any three elements of V. And now the logical structure of the theorem. If, right, keyword, what's the condition? If this equation holds, X plus C equals Y plus Z, then it must be that X is equal to Y. So you can quote unquote cancel the Z's in a vector space. Right? It looks trivial, but again, we're doing this about some abstract vector space. We have to prove it from the axioms. We have nothing else. We have no other results about these things. So we can't just say, well, yeah, that's true because it's true in real numbers. This might not be the vector space of real numbers. You know, maybe it's one of those examples we just talked about, the vector space of functions or the vector space of matrices, or maybe it's some vector space I've never heard of. And I still want to know that this is true, that this property is true. So I have to derive it from the axioms. All right, so what do you think the relevant axiom is? What can we do? You have to kind of stop and look. I don't have a list of them here for you. You can go back to the other video or pick up your ebook, your PDF, check them out. What do you think we need to do? All we can do is proceed with those things. So one of the axioms says that there's this thing called Z prime in the axioms, right? Z prime, it exists. I'm going to use shorthand here in this little informal computation. So there exists some Z prime in V that when you add it to Z, you get the zero vector. Every Z has such a Z prime. So to X, so to Y, but I'm picking on Z because it's in both sides of this equation. So you see, if I took something like X, it's certainly the same as X plus zero, right? Every vector is itself plus zero. And the reason I'm doing that, I'm kind of trying to be a little tricky here, but that zero is Z plus Z prime. I'll parenthesize it to emphasize that. Does that make sense? So zero is Z plus Z prime. It's a little bit in an out of a hat statement. I mean, there's other ways I could think about this, but I'm just trying to proceed by the axioms. Right, so I'm not going to sit here and delineate them all. I don't have the list in front of me, but this is some vector space axiom, the third one, I think. This is just substitution. Zero is equal to that thing. But now I'm going to use one of those associativities, maybe the second vector space axiom, if I'm not mistaken, says that I can think of that added like that. But by our hypothesis, X plus C is Y plus C. You guys see what I'm doing? Stop the video and finish this without me. Now I just reassociate one more time, slicko, and remember that that parenthesis thing is zero. And look what we've done. At the end of the day, we were able to deduce that X was the exact same thing as Y. Yeah, and that's what the theorems claimed. Neat. All right, so that's sort of a discussion of the proof, same proof the author gives in the book. The author has a couple of corollaries. They're left as exercises. I think I might leave them too. One of them, maybe just to talk about what the statements mean. They're stated a little bit colloquially that zero is the unique element satisfying vector space axiom 3. So it means that if you had some other element So that's what it means. It means that if some other element, let me just call it 0 tilde, if it also satisfies vector space axiom 3, then it must be the case that it's the same as R0. That's what corollary 1 is. So you're gonna get to think, how are you gonna get that out of the cancellation law? That's the secret. I'm not gonna prove it. I'm gonna leave it to you. Corollary 2 is that x prime, the element that you add to x to get 0, it's unique. Yeah. So what does it mean if you had some other imposter, x prime imposter, that also added to x to get 0, that they have to be the same? So if this thing also satisfies vector space axiom, I'm not going to write it because I don't know. Well, it's 4. Yeah. So if this thing, actually, I'm not writing this correctly. My brain is getting tired, and I should stop here. That if these two things both satisfy vector space axiom 4, then they're equal to each other. Sorry, that took me a while to spit that out. That's what I was trying to say. Nice. Okay, so we have a little bit of work left here to do. One more theorem. It's got 3 parts. I'm tired. I'm not going to do all of them. I'm just going to try to talk us through what it says. Hopefully these proofs are something that are approachable. You can talk to me about them in office hours, but these are good things to get us all sort of refreshed and back on the same page. But let's see what it says. So you have a vector space V over a field F. Then this first one, I'm not going to give a proof, but I'll talk you through it. It says that if you take any vector and you multiply it by the 0 scalar, you get the 0 vector. All right. Take any vector, multiply it, and the proofs of these are written in the book, by the way. You take any vector, multiply it by the 0 scalar, and you get the 0 vector. How do I know that this is the 0 scalar and that's the 0 vector? How do I know that? It has to be from context. X is declared to be a vector. 0 scalar and 0 vector are denoted the same way, but this can't be a vector, the 0 on the left of the equation, because what would it mean, vector times vector? We don't have such an operation. So this must be the 0 scalar. Our notation is a little subtle. But this side's a vector because of the scalar multiple of a vector. So this side, the other side's a vector too. So that's how I know that's the 0 vector. All right. Yeah, check out the proof in the book, but before you do, try to prove it yourself. Try to use the cancellation laws. We're going to prove B. What does B say? It says that if you take a vector and a scalar, then the opposite in the field of that scalar times the vector is the inverse. I'm denoting by x prime minus. It's a better notation. And the other way around, the scalar times the opposite of x. Okay? What's the third one? You take any scalar and multiply it by the 0 vector, right? You have to get the 0 vector. There, I should be a little bit, that's a little sloppy, because this could mean 0 times 0 in F2. So here I mean the 0 vector. The notation's ambiguous. And if I mean the 0 vector on the left-hand side, then I don't have to say I mean it on the right-hand side, because the vector can't be equal to scalar. Good. All right, so how to prove B? Well, this thing, minus AX, the new name for AX prime, it's the only element that satisfies this equation that I've got written there. Yeah. So that if you take some other element, if I take AX and say add to it what was the proposed candidate, it's minus AX. Let's look at this thing. Well, by the distributive law, vector space axiom something or other, this is the same as A plus minus AX. But that's 0x, and then well, I'm borrowing from above, but that's equal to 0. So what does that mean? That means that this thing, the opposite of A times X, is doing what that unique element does. Well, by uniqueness then, this thing, the opposite of A times X, has to be the same as the opposite of AX. Okay, so I'm going to leave the other one to you. The proof technique is the same. This video is getting kind of long, and maybe in the in-class session, we could have had a chat about it. All right, so thanks for listening.